So we've talked about hydraulic conductivity of soils, and we know that if we draw a plot, and on this axis we'll have the conductivity, and we'll know it goes from 0 up to the saturated value. And on this axis we'll put the water content, which we use the symbol theta, and it's going to go from the saturated water content, and then we'll say this is the residual water content. We remember that this has a strong downward curve. So the conductivity drops very quickly with water content and, and goes to a value of 0 when the soil is not entirely dry, but the films have broken down. How do we describe this? Well, one of the ways that people use to describe this is with a simple Gardner equation. So the Gardner equation, well, the Gardner exponential form of conductivity approximates the conductivity at any given pressure with the saturated conductivity times the exponential of some alpha times that pressure. Okay? Now the first thing we notice is that here we've represented moisture content versus conductivity, which is the usual form. Here we're representing actually the conductivity versus pressure. And when pressure was equal to 0, then this is equal to K sat. And as pressure grows, this diminishes. So in fact, we can just put K sat there and put K equals 0 here. And now we can dispense with using this right-hand axis and just put everything in terms of pressure and on this axis and conductivity on this axis. So we still see a rapid decrease in conductivity, in this case with pressure, and it has some sort of decay where when H is equal to about 1 over alpha, this is equal to about 34% of the original K sat. And so again, if we go another value, and we can remember these, so H equals 2 over alpha, then we've decreased it down to about 5%. Okay, so this is the structure as this goes from a value, and keep in mind that H is negative here. That's negative pressure. So as this goes to 0 to -1, this whole term, it's about 34%, -2, etc. So it's a classic exponential decay. Okay, so the question I have for you is, how do we know what this value of alpha should be? So in this conductivity function. And I'm not going to tell you an exact way to get it, but I'm going to give you what I think should be a convincing strategy. So now going back to our moisture characteristic curve, which is plotting moisture content versus pressure. Remember, it looks something like this. And what we can say is that we know that this conductivity dropping dramatically has to do with this moisture content dropping. So the conductivity is dropping here, and so we probably got to this moisture content to have it get to its 34% of original conductivity, right? So we now can say, aha, it's a fairly small change in moisture content that we saw, certainly compared to the whole range. So we can see with some small change that we would probably get our big drop in hydraulic conductivity. So if this is the draining curve, what we can do is identify, aha, this point here is something like just bigger than the water entry pressure, the air entry pressure, excuse me. And so what we can see then is that alpha, if we call that H air entry, then H air entry is about equal to 1 over alpha. So this gives us a little bit of an idea of if we're going to represent conductivity as a function of pressure, which is often very convenient, then we can identify the value of this parameter is something related to the pressure at which a lot of air starts entering the soil, disrupting the primary flow paths, creating a great decrease in hydraulic conductivity. And so this Gardner exponential form of the hydraulic conductivity is very, very handy for many calculations because it creates a linear differential equation oftentimes. And we can identify the value of alpha fairly conveniently. But of course, what is the risk of using this method? The risk is that we are putting it in terms of pressure. And if we were to have, this is a draining curve, if we were on a wetting curve, the water content might be like this. In this case, at that same pressure, we'd have a very different water content and a very different hydraulic conductivity. So the danger of using this is it doesn't deal with hysteresis. So watch out, it's very convenient. We can estimate the parameter values very well, but representing conductivity in terms of pressure has the risk because we're not representing it in terms of the fundamental variable, which is the water content, which actually dictates the flow paths.